Hello students. Today we are going to take up a new topic, and this is a topic which is not usually covered in standard textbooks. So, I want you to pay special attention to the topic that I am going to discuss in today's class and the next lecture. And the topic is stability of thermodynamic systems. And the system that I have in mind for this particular class is a non-reactive single phase system, such as an ideal gas, a single component ideal gas. So, you have 1 mole of argon gas at a very high temperature. So, it acts as an ideal gas. So, you say that okay, what I have is a non-reactive single phase, because there is only the gas phase of the substance of your system, and it is a macroscopic system. Therefore, I can use the thermodynamic description for this, and I am going to ask this question: if I am writing down the equation of state P v equal to R T for 1 mole of this argon gas, is it going to be stable in the gas phase for all values of pressure, volume and temperature for 1 mole of this substance? When I say stable, I mean it is going to be stable in its gas phase, in that single phase with which I have started the discussion. The other question is, okay, do I have to restrict myself to real gases, to ideal gases? Obviously no. I can have real gases. For instance, when I am talking about a van der Waals gas, I can write down the equation of state, all of you know that. Then the question would be, if I go on cooling a van der Waals gas, will it always remain a gas? You know the answer. The answer is, if I cool a gas at constant pressure, in that case at some point below certain temperature, the gas will undergo liquefaction, and then the liquid phase and the gas phase will coexist in equilibrium if you maintain the condition of phase equilibrium. So, the meaning is, the initial single phase that I started with, that is no longer stable under the given condition, and as a result of the instability of the system, it has decomposed into the liquid phase and the gas phase, which under the given experimental condition will give me the system coexisting in equilibrium in 2 phases compared to the single phase that I started from. So, as you see that, then the question that comes is it possible to give a thermodynamic basis of this observation that some systems are stable in a single phase and for given experimental condition, but some other systems may not be stable in a single phase. So, in today's lecture, I will give you a general framework of how to set up the condition of stability of a given thermodynamic system based on whatever we have learned in this course so far. So, let us go ahead and remind ourselves the condition of a spontaneous change in state. So, what I have already told you is that any natural change within an isolated system is accompanied by an increase in entropy. So, what happens is, you start from an initial equilibrium state, then you allow the system to undergo a change in state. Then there will be an increase in entropy, and the entropy will continue to increase as long as the changes occur within this isolated system, and eventually when the entropy attains its maximum value, the system has reached a new equilibrium state. So, we have seen this picture where if this is your initial equilibrium state and you are asking the system to undergo a change in state, it will always go towards the direction, spontaneously it will always go towards the direction where the entropy is increasing, and the change will be arrested when it has reached the maximum value of entropy under the given condition. And we also give you this list which actually summarized that if you start from an initial equilibrium state and induce the system to undergo a change in state, then ds greater than 0 is corresponding to a spontaneous change in state which is irreversible in nature. ds equal to 0 is a new equilibrium is reached. But in today's lecture, I am going to look at this particular condition. This is ds less than 0. So, if you have a system in a given equilibrium state and then you are trying to induce a change in state that is associated with a decrease in entropy, then you understand that this change in state will not take place spontaneously. And therefore, I would immediately say that this system under the given influence of the external whatever influence you are having on it to induce the change in state, it does not care. The system is stable in its equilibrium state with respect to whatever you are doing to induce a change in state. Therefore, as you see that the condition of the process not being favored is actually the condition that the system is stable in its initial equilibrium state. So, based on this idea, we will go ahead and think about the condition of intrinsic stability of a system. And to start with, I have taken an isolated system which is comprised of two identical subsystems. Now, let us have a schematic diagram of this. So, what I have is one compartment 1 which is isolated from the environment, another compartment 2 which is also isolated from the environment, and these two compartments 1 and 2, they are separated by an adiabatic rigid impermeable wall. As a result of this, as you see that I have two identical subsystems by construction. So, the equilibrium state of compartment 1 will be given by u v n, and the equilibrium state of the compartment 2 is given by the same values of u v n. Okay. Then under this condition, I would say the entropy of the compartment 1 would be some function of the values of u v n, and S 2, that is the entropy of the compartment 2 under the given conditions, it will be the same function of the same values of u v n. Therefore, if I now want to make a plot like this, that I am plotting u as a function along the x axis and s along the y axis, let us say that this is the how s varies when u varies. So, this is just a schematic diagram. So, I find that when any of these subsystems has this value of u for its internal energy, this is the value of S as predicted by this curve, which shows the functional dependence of entropy on u. And we also realize that the entropy of the system in its initial equilibrium state, where compartment 1 and compartment 2 are not only isolated from the surroundings, but are also isolated from each other, but they are identical. In that case, I would say that S initial is equal to S 1 plus S 2, and this basically says that S initial is equal to 2 into this value of entropy for the given value of u, v and n. So, in this case it is 2 times the value that I have shown here. Now, moving ahead, what I will do is I will make this separating wall between 1 and 2 slightly diathermal. So, the nature of this wall changes, and this will allow the transfer of internal energy from delta U internal energy of delta U from 1 to 2 say. So, in this case what will happen is the internal energy of compartment 1 in its new equilibrium state would be U minus delta U, and internal energy of the compartment 2 will be U plus delta U. The other parameters like V and N will remain the same, because the wall is still rigid and impermeable. Okay. So, then the new value of entropy for compartment 1 is going to be S1 prime, which is the same function of S evaluated now at U minus delta U. And similarly, for the second compartment, the entropy will now be S2 prime, which is the same function S evaluated now for U plus delta U. Then I can say that the entropy of the system in its final equilibrium state will be given by S1 prime plus S2 prime, and that will in general be given in terms of the explicit value of S evaluated at U minus delta U and explicit value of S evaluated at U plus delta U. Now, in the next step, let me visualize what this S1 prime and S2 prime are. So, this point is U minus delta U, and therefore, this is the value of S1 prime. Now, let me have the same point U plus delta U, and that gives you this is the value of S2 prime as per the functional dependence of S on U. Therefore, I can now connect these two red points by a straight line, take its midpoint, and this gives me that this is at the same value U, but now its value is half of S1 prime plus S2 prime divided by 2. Now, how am I going to use these values? I understand that under the given condition, the change in entropy of the system is S final minus S initial, where S initial is 2 times S evaluated at U and S final is S1 prime plus S2 prime. So, if I now write down delta S, I can very easily see that delta S is 2 times half of S1 prime plus S2 prime minus S. Okay. So, now let us have a look at the quantity written within the square brackets from this expression. So, this is the magnitude of half of S1 prime plus S2 prime, and this is the magnitude of S. So, what do I observe from this particular diagram? I find that the green point is higher than this red point over here, and that means that I must be having half of S1 prime plus S2 prime greater than S, and that basically says delta S is greater than 0. So, what have I learned from here? What I have learned is if the entropy has a functional dependence as shown by this purple curve over here, then if I allow an exchange of internal energy such that the compartment 1 loses internal energy delta U and compartment 2 gains it, in that case what happens is there will be a spontaneous change in state with respect to energy flow from 1 to 2, which means in other words that if the variation of entropy with respect to U looks like this, the system is not going to be stable in this range where I am looking at the fluctuation of U from U minus delta U to u plus delta u. Okay. Now, let us consider another system where I have carried out the same experiment, but now the variation of entropy with respect to u has some other functional form. Okay. So, as before, I will have delta S equal to 2 into half of S 1 prime plus S 2 prime minus S. Now, with this very different change in the functional dependence of S on u, let us now check what would be the sign of this difference. For that, I will have to look at this point which corresponds to my u minus delta u. Therefore, this is the corresponding value of S 1 prime by definition. Now, I will also have a look at the second point over here which corresponds to u plus delta u, and this is the value of S 2 prime. Now, if I join these 2 points by a straight line as before, and I see that this is the point where what its value is going to be corresponding to u, I find that this must be the point where S 1 prime plus S 2 prime by 2 is the value of entropy. Okay. Now, from this diagram, what is it that I have learned? I have learned that in this case S 1 prime plus S 2 prime by 2 is less than the value of S when evaluated at same u, and that tells me that there will be a decrease in entropy as I allow the system to transfer delta u amount of internal energy from 1 to 2. And then you would say that since this quantity is negative, therefore, in this case delta S is less than 0, or it may so happen depending on the functional dependence of S on u, it can also be equal to 0, but in both the cases what you will see is the transfer of internal energy will not be spontaneous, or in other words, the system will be stable in the state u v n with respect to energy flow between 1 and 2. Now, you see that I am trying to have a condition of stability of the system which is intrinsic to the system, or in other words, I am trying to express the stability of the system in terms of some internal property of the system or the state function of the system, and therefore, what I have said till now is as follows. For an isolated system in the state u v n whose entropy is expressed as a function of u v n, the condition of stability with respect to exchange of internal energy u would be given by, this is the final entropy minus 2s u v n, that must be less than or equal to 0. Okay. Now, how will I find out this kind of behavior? One way is if you know the fundamental equation of the system, where you know the functional dependence of S on u, it is very simple. You plot u along the x axis, you plot S along the y axis, and then you look for a pair of points B G, and you see that the entropy curve that lies below this line. And this is the situation where we have seen that the system will be unstable. Okay. Therefore, this is an unstable segment of entropy between B and G. So, if you are maintaining the system at some values of u between B and G, the system will not remain stable in a single phase. That says that this condition is actually a condition of global stability, and it says that there should be a concavity of entropy. Here, as you see between these two pair of points, the entropy is not concave, it is convex. As a result of this, this is an unstable segment. Now, moving ahead, I would also see that in the unstable segment there are two different segments over here. Here you see the entropy is decreasing with increasing u, here entropy is increasing with increasing u. But now you know that del S del u V n, that is 1 by T, okay? And therefore, whenever you see a segment like this, that implies as if you are having negative temperature, which by the formulation of thermodynamics is not allowed. So, that tells me that although the global stability of this entire segment of entropy is understandable, I probably should look into the local slopes over here to understand locally what is the condition of stability. Now, in order to derive the local condition of stability or instability, as you want to call it, I will take the limit of delta u going to 0. Now, in the limit of delta u going to 0, I can use a Taylor series expansion of this quantity. I can write down S when evaluated for u minus delta u, that would be written as the unperturbed value of S minus the first term involving the term linear in delta u. Therefore, I will have del S del u V n as the first derivative term appearing over here. Similarly, that is the second derivative term I have written down here, which involves the delta u square. And since I am interested in delta u going to 0, I will have enough reason to truncate the Taylor series after this term. I can similarly write down the corresponding Taylor series expansion for entropy evaluated at u plus delta u. So, as you see the changes over here, here I had a negative first order term in u, here I have a positive first order term in u. So, if I now evaluate, I add these two equations. On the left hand side, I have S evaluated at u minus delta u plus S evaluated at u plus delta u. And obviously, on the right hand side, these first order terms, they get cancelled and I am left with 2 S in the unperturbed state plus the second derivative of S with respect to u into delta u square. So, now you see, if I compare this equation with this equation, I have an analog of this global condition in the limit delta u tending to 0. And therefore, I will find that S u minus delta u V n plus S u plus delta u minus this 2 times S unperturbed, that is directly dependent on this local curvature of the curve S when plotted as a function of u multiplied by delta u whole square. Now, the condition of stability is given by the sign of this term, and as I know that delta u is not equal to 0 and it is a square term, therefore, the sign of the left hand side will entirely depend on the sign of this second derivative. Therefore, I can say that the condition of stability with respect to infinitesimal exchange of internal energy, that is given by del square S del u square under suitable constant condition must be less than or equal to 0 for the system to be stable locally. Therefore, under this condition, I find that this entire segment is globally unstable for entropy if the red curve represents the variation of S with u, and I also find that here the curvature is positive. As a result, I will say that the system is locally unstable along this particular region as I have shown here. So, now that I know what is happening for an isolated system in terms of entropy, I can again say that well, the condition of stability with respect to exchange of internal energy and volume V is given, and in the limit where I can allow the fluctuation of both u and v, that is the volume, I can say that delta S should be less than or equal to 0 for a stable system, and the corresponding relationship in the limit of delta u and delta v going to 0 turns out to be involving the expansion of this quantity in terms of a two-dimensional Taylor expansion, two variable Taylor expansion, where I not only have the entropy at the initial point and the first order terms in each of the variables, but also the pure second order terms for each of the variables and one cross term over here. So, I can use the same I can use some simplification in the representation of these. So, what I have done is this second derivative I have replaced as SUU. So, this is a shorthand notation of del square S del U square. Similarly, I have SVV. This is a shorthand notation for del square S del V square. Then automatically following the same notation, SUV becomes a shorthand notation for del square S del U del V. So, now going ahead, I can write down S evaluated as at U minus delta U. I can write down S evaluated at U plus delta U, and correspondingly I can find out that the condition of stability which involves this quantity, that would be given by SUU delta U square plus SVV delta V square plus 2 times SUV into delta U into delta V. Now, we will play around with this relationship, and then we say that in the limit of delta U and delta V going to 0, the stability condition is now dictated by these 3 partial derivatives. Okay? And I can very easily do an algebraic manipulation and rewrite them like this. And I note that in this case delta V is non-zero and positive, and therefore, this condition in the limit of delta U delta V turns out to be SUU SVV minus S square UV must be greater than or equal to 0. So, if I write down explicitly the definitions of the second order derivatives, I find that if you are given the fundamental equation S as a function of UVN in a given particular system, in that case what happens is you must have this condition satisfied for the stability of the system. Okay? So, it says that global stability requires the entropy surface, that S as a function of U, to lie below its family of tangent planes. Okay. Therefore, you can have a simple visual or mathematical examination of whether a given function of entropy is mathematically viable to represent a stable state of the system, and the local stability requires that this curvature must be less than or equal to 0, this curvature must also be less than or equal to 0, and then this must be greater than or equal to 0. So, in this class what we have shown is how to derive the condition of stability in an isolated system, both globally and locally. And what is it that we have used? We have just used the simple fact that in an isolated system, a negative change in entropy is never spontaneous, as a result of which the system will prefer to stay in the equilibrium state where we have prepared it. We will continue our discussion in the next lecture from here. Thank you.